Welcome. This is Terry Fox. We're going to be going through a DDR3 2133 memory circuit design tutorial. This first video is the introduction. This sort of gives you the background so you understand how these circuits work. I graduated from Montana State University a long time ago. If you'd like to know about my consulting business or the training classes I do, you can go to www.siemc.com and there's more information on that. But here we go, DDR3 2133. In this design tutorial, this will be an ongoing effort. We will go through how DDR3 memory really works. If you understand how it works, it is a whole lot easier to physically lay out the design. Now, there is safe DDR3 routing practices, and there are ways that I would say can work, but they lead to problems. So what I'm going to do is try to explain to you what are the safe routing practices. Another thing you'd better understand right up front is that you must simulate. These things are not inherently terribly difficult, but it's a little bit about a question of can you see what you're doing. And when we go through this, you'll understand what I mean. DDR3 timing requirements, so we put some real numbers behind things. Some big no-nos. I have seen some of the most miserable designs on the planet that were places where someone copied a design example, and the design example was a lousy example in the first place. So please don't just copy design examples. Look at them for reference, but if you don't understand how this stuff really works, doing something blindly will end up with a lot of problems. Now we'll talk about the steps necessary to build reliable 2133 designs, making systems work together. I'm actually going to have 3 examples whenever I get this thing done. The first one is a DDR3 2-chip solder-down memory system. This first example means that I don't have to deal with SODIMMs or connectors. The notion here is learn to walk before you run. The second example will have one SODIMM. There we start picking up connectors. The third example will have 2 SODIMM sockets, and that's where we're dealing with multiple sockets, heavy address and control bus loading, and also the interactions that come between those sockets. So here we go. DDR3 is based on 3 key concepts. First, divide and conquer. There are actually 9 clock signals in a 64-bit DDR3 design. Address, command, control are clocked by the master clock. The 64-bit data bus is divided into 8 byte lanes, each of which has its own clock that we call the strobe, the DQS/DQS0 data strobe, to clock in those signals. So in this way, when I have to do length matching, I can break up my length matching requirements into the address, command, and control group, data byte 1, data byte 2, data byte 3, data byte 4, data byte 8, etc. And that way, it makes it much easier to route these signals and to make these things work. The second key concept is this idea of right leveling. And at boot time, your controller will basically send data out to the SDRAMs and then look at and then read that information and try to ascertain what is the correct time of flight for each one of those byte lanes. Now, in that way, we can normalize the relationship between the master clock and the 8 DQS strobes that are in there. The difference in time of flight is a direct result of the load-terminated daisy chain, i.e. flyby routing of the address, command, and control signals. This also makes the design much easier to route because tight length matching only applies across a single byte lane or a single group. Now, the third concept that makes DDR3 really wonderful is this idea of on-die termination and programmable drive strength for the data group. Now, that eliminates the need to have resistors on the board. Now, if I look at just any clocked memory system, we've got the notion of a clock or a strobe which defines when the signals are to be latched in. So if this is where the clock goes down, then I know that there is a time before the clock we call the setup time, and a time after the clock that we call the hold time, and as long as that signal is clearly above the upper limit or below the lower limit in that setup and hold time, then fundamentally we're golden. Now, if I was looking at the address and command lines, then this would be the master clock. If I was looking at DQ0 through DQ7, then it would be strobe 0 would be the time demarcation point. If it was DQ24 through 31, well, that would be strobe 3 that is this demarcation point. But what I've got are actually 9 individual little buses, if you will, that make up the entire 64-bit design. Now, if you understand that part of it, that we have to have this setup time and the hold time, and that the clock is basically falling in the middle-ish part of that open eye, and that anything in a particular group has got to overlay. So all of the address, command, and control has got to basically have the eyes open up at about the same time. For the data bits 0 through 7, they've all got to open up at the same time. Now, if we get past this idea of having an open eye, a clock, setup time, hold time, the next thing that we've got to understand is the language that they use in DDR3. When we talk about VREF, we're talking about basically 0.075 volts, which is halfway between the 1.5 volt power supply and ground, and that is the center of this data eye, if you will. Now, if I go up 125 millivolts, that's called AC 125 if it's on the leading edge, and that is associated normally with what we talk about as the specification on a setup time. Now, if I went up to 135 millivolts, then that would be called AC 135, 150, 175, and all of these have got different timing requirements for the setup time. If I look at the hold time is always related to one particular point. It's called DC 100, and that means from VREF you're 100 millivolts above VREF or 100 millivolts below, and those are the places where we're actually going to look for our timing numbers. So understand that these are DDR3 speak, and if you understand what these mean, it'll be much easier to read the data sheet. Okay, next. These designs are conceptually easy to lay out if you can do the following. If I look at the master clock, the address, command, and control group, which I'll call ACC, address, command, and control, these things need to be routed in a daisy chain load terminated fashion. Now, if it's address, command, and control, we will typically go controller, first SDRAM, second SDRAM, a load terminating resistor, and that ties into VTT, and VTT is halfway between power and ground, so that means it is 0.75 volts on standard DDR3, and that is a real power supply. Now remember that VREF is also 0.075 volts. Please do not connect VTT to VREF unless you decouple VREF a bit. VREF is a reference voltage. VTT is an honest-to-goodness power supply, and it's second in importance only to the actual driver power supply, the 1.5 volt power supply for DDR3. So controller, first SDRAM, second DRAM, SDRAM, load termination, VTT to 0.75. Note, the master clock is commonly load terminated with a resistor from CK to CK naught. So this would be a standard LVDS termination sort of scheme, and that's just fine. I like to tie the center of these to VTT, but it's not necessary. You can, as long as you've got symmetrical clocks, then you can certainly just drop the single CK to CK naught resistor there and it'll work just fine. Now, the signal must be clean and unambiguous at the receiver. I need to make the die-to-die time of flight for the clock, for the address lines, for the command lines, for the control lines. All of those have got to be roughly equal, including the time of flight on each layer, the time of flight inside the IC package for pin to die, the effect of vias, the effect of ringing, the effect of crosstalk, jitter, and the effect of any power delivery system or signal pattern induced noise. So as long as I can do this, these things are really very nice systems, and they work like a champ. Now, these designs are conceptually easy to lay out if you can do the following. Here we're talking about the data group. So within a specific group, the group members should be the same time of flight. So if I look at everything that's associated with data strobe 0, that would be data bits 0 through 7. Those should have the same time of flight, die to die. Now, one of the benefits that we've got is that in the data group, I've got controlled drive strength on the driver's side, and I've got on-die termination on the receive side. And since the data group is bidirectional, then that exists both in the controller and also in the SDRAM. Now, something to note about pin swapping: if you want to swap data bit 0 for data bit 7, that is not a problem. These are both in the same byte lane. Now, if they're in the same byte lane, you can swap those, and there's absolutely no problem with that. Now, on the other hand, if you try to swap data bit 0 for data bit 8, that does not work, because data bit 0 is referenced to strobe 0, data bit 8 is referenced to strobe 1. So keep that in mind, but pin swapping a lot of times will help you route these things much easier. Now, these are point-to-point signals, and ringing is controlled through the drive strength and the on-die termination, this scheme over here. Now, the bit order can be swapped as long as they remain in the same byte group. You must find a combination of drive strength and on-die termination that gives a clean open eye with minimal ringing. I really recommend that you check this out up front. I have found some on-die terminations that don't seem to work as well as they should. I end up with ringback. It's good to spot that stuff right up front. Now, there's an alternative routing scheme for address command and control group. That is, if you want to use the DDR2 scheme that was a balanced T routing for address command and control, that's fine. But let me tell you what the requirements are. First of all, from the split point, this distance and that distance, and I'm talking about time of flight to the die, those distances or those times of flight must be equal. The second part of the requirement is that if this is address 0, then the time of flight from here to here, which by the way should be the same as the time of flight from here to here, that time of flight needs to be the same as the time of flight for address 1, address 2, address 3, address 4, etc., etc., etc. Okay? So if you want to use balanced T, and I have seen sample designs that do it this way, they will work. It's just that I don't recommend this technique because it's a pain to get all of the T's in equal, in addition to getting the overall timing of the group equal on a die-to-die basis. And due to the inside the package variations, always validate the design with the exact port stackup and the pin correct IBIS models through simulation. That's the way you make sure this all works. Now let me also point out, you can paint yourself in a corner with this balanced T type thing, where it becomes progressively more difficult to solve the routing problem, and in fact that's the reason we went from DDR2 to DDR3, or one of the driving factors behind it was just the amount of time that layout designers were spent in routing. Okay, so that's it for the introduction. More slides to go, but that's it for now.